When dealing with equilibrium, particularly linked equilibrium, it's useful to manage the equations, combining them and altering them to create a combined equilibrium statement. Particularly when you have two reactions that are either competing with one another or producing mixtures of products. Very common in acid-base neutralization, for instance. And so we can create a new equilibrium statement out of other equilibrium statements by combining them, using many of the ideas that we experienced in thermodynamics to create new reactions. So let's take a look at an example. And the main thing we're going to be doing is we're changing stoichiometry or reversing a reaction, or combining two, adding reactions together. So how do we do this? So let's take a look at a target example. You can easily prove that when you change a reaction, stoichiometry or arrangement, it has an effect on the value of the equilibrium constant. So let's take a look at, so we have a target chemical reaction, and we want to know what the value of the equilibrium constant of a related chemical reaction is. And then we have to compare these two reactions and see how they are similar. And so we see the equilibrium constant is 5.5 times 10 to the minus 2 for this reaction. We can see that the difference between these two is stoichiometry. We've multiplied this reaction by 3 times the amount to give us 3 times the stoichiometry. But the equilibrium constant for this has a different form, whereas this one's value is NO squared divided by N2 divided by O2 equals K. This one's equilibrium value is not the same, even though we've multiplied the stoichiometry by a factor of 3. The equilibrium expression is not multiplied by 3. In fact, the relationship between this equilibrium expression and this equilibrium expression is the relationship between this equilibrium expression and this equilibrium expression is not a factor of 3, it's a power of 3. So we raise the equilibrium constant to the power of the stoichiometry in this case. So we multiply by 3, and so we raise the equilibrium constant to a power of 3. So it turns out that K1 would be equal to K raised to the third power. And so if we take K and we raise it to the third power, we see that that becomes NO to the 6th, N2 to the 3rd, and O2 to the 3rd, which would be equal to K to the 3rd, which would be equal to K1. Exactly the same form. So we've just proven that that works. Doubling the stoichiometry, we'd square the equilibrium constant. Tripling the stoichiometry, we'd raise it to the third power, etc. Cut it in half, take the square root. Cut it by thirds, take the cube root. Right? So relatively simplistic procedure. Reversing a reaction is very similar. So let's take a look at another target. NO. How do we go from here to this target reaction? NO goes to 1/2 N2 plus 1/2 O2. Again, how are they similar? Well, these reactions have the same components, but they're flipped. And so we reverse the reaction. Reversing the reaction would mean that we reverse this reaction, the equilibrium constant is flipped. All right? So it's the inverse of the equilibrium constant. So we know that it would represent this reaction reversed. 2NO is in equilibrium with N2 plus O2, and the equilibrium constant for this reaction would be 1 over K1, 1 over K. And what do we do to make this reaction look more like this one? We'd have to take half the stoichiometry, and so this one we would take the square root of K1 equal square root of 1 over k. Which is our target reaction. Now we can prove this explicitly if we write the form of this reaction, which is N2 raised to the 1/2 power times O2 raised to the 1/2 power, all divided by NO. This will equal some k, we'll just call it k prime, call it k double prime. And we can see that the relationship between k and k double prime, the equilibrium constant for this reaction, is relatively easy to generate. And once we have that, we can show that k double prime is equal to the square root of 1 over k. Because if we take this reaction k and we inverse it, 1 over k will equal N2 O2 NO squared. And if we take the square root of both sides, that becomes N2 1/2 O2 to 1/2 divided by NO. Which is equal to our target reaction. So this allows us a way to check our values. Most of the time you don't have to go this far. The mathematical symbolic relationship is usually enough. But if you're unsure, like say on a homework, work it out the long way.